This is our quantization condition, so let's see what it tells me about these objects, phi and about this phi and phi star. This is phi. I know I had calculated the canonical momentum corresponding to phi. It's just the time derivative. This will be dp over square root of 2 omega p minus I omega p phi of p minus e to the power I omega p of t This is my momentum. Let me calculate their commutation relation. Well, I have two integrals.
Under what conditions I, take the time derivative inside the integral?
Are there?
Under what conditions, because I take the derivative of the phi.
Well, it should be smooth, and I will take the integral should converge. The convergence should be in a particular way, etc. If you talk to a mathematician, they will list the conditions. But in physics, we always assume that they are satisfied. So we almost always just exchange the order of integration and derivation, because our functions, we assume them to be smooth enough. Does this cause problem? Sometimes, but when the problem arises, we try to solve it. Not before they arise. So that's why mathematicians don't so much like field theory. I mean, you see, we will have more serious problems with infinities, for example. And so let's just proceed. Okay, I'm just lazy to write down everything. So I will start by saying that phi p and phi star. Phi p at different p's, they commute. Phi stars at different p's, they will also commute. So when I'm writing these commutation relations, I will ignore the commutators of phi p with phi p prime, phi p1 with phi p2, and phi star p1 with phi star p2. But I just leave the commutators of phi and phi star. They need not commute, and we will see that they don't actually commute. And there is a more formal proof that phi p1 and phi p2 do commute, but as I said, I don't want to write it down all down. So let's see.
So phi are operator valued functions. Is phi are operator valued functions? Because we say they are commute.
You see, what we are, let's follow. When we quantize, let's say, this system of oscillators, we have the x and p's. They both depend on the position. For every oscillator, we have a different x and a different p, and we say that they, when we quantize them, we say that they don't commute. Their commutation is this minus I. Well, we are basically doing exactly the same thing over here, but instead of talking about the position of oscillator, we are still talking about the position, but the position we are showing as y rather than n or m. The position doesn't go as 1, 2, 3, 4, it just goes as y. And we have different oscillators at different y values, and we are, in a sense, different positions. Now the displacement, the x's became phi. You see, I or n became y. This is a discrete case. This is the continuous case. xi just became phi y, xn, sorry. Pn just became py. So x is an operator, xn is an operator, so is phi y. Pn is an operator, so is py. Y's are the positions, so at every position, in a sense, we are assigning an operator. So yeah, they are operator-valued functions. So that's what a function does. So you give it some numbers, it gives you something else. So in this case, what it gives me back is an operator with one component, and hence it's a scalar operator. This operator will be Hermitian, and hence it's a real scalar operator, or real scalar field. Okay, so let me go back to this commutator. I have minus I omega p1 e to the power minus I omega p1 of t plus I p1 of y1 phi of p. This is from the momentum, and I have the phi star term from the field itself, e to the power I omega p2 of t minus I py phi star of p2. And then I have the other cross terms, phi star of p1. This is from the momentum operator. From my phi operator, I get the first term, not that one. This one, so which is e to the power minus I omega p2 of t plus I py2 phi of p2. And remember, this should be equal to minus I.
Minus I or minus I times delta?
Minus I times delta. Which, by the way, can also be written as dp over 2 pi e to the power I p y1 minus y2.
What's omega? Omega, dp over 2, capital omega.
Where?
The last, the last expression in the integral. dp over 2.
It's pi.
Where's pi? Sorry.
Pi. The last equivalent. dp over 2 pi.
2 pi. Yes, this is my pi.
Omega.
No, this is pi. Well, let's see how can we convert the first one to the second one. Well, let's see. These omega p's, I have an omega over here. I have 2 omegas under the square root. They would cancel, let's start with, they would cancel nicely if I would have p1 is equal to p2. Right? And if you look at these exponents, if p1 is equal to p2, let's say in this exponent is multiplied with this exponent, if p1 is equal to p2, the time-dependent parts would cancel. They're at the same time t. The y-dependent parts will be I p1 y1 minus y2 if p1 is equal to p2. So they would nicely cancel. Well, the same thing will hold for the second one. if that term is also proportional to some kind of a Dirac delta. So let me make the assumption, start with the assumption that phi of P1, phi star of P2 is equal to some number, let me put n, Dirac delta P1 minus P2. If that is the case, look at the top part of the screen. Pi of y1 of t, phi of y2 of t would be equal to dp1 dp2 divided by 2 omega p1 2 omega p2 minus I omega p1. Then I have the first exponent, the first term in curly braces would be e to power minus I omega p1 minus omega p2 of t plus I p1 y1 minus I p2 y2 Dirac delta n times Dirac delta p1 minus p2. N is the normalization, it's not a function, it's the normalization. N times Dirac delta. And then I have the second term. You see, the second term is the commutator of phi star and phi, so I get an additional minus sign. So that becomes a plus omega p1 minus omega p2 minus I p1 yy plus I p2 y2 and Dirac delta p1 minus p2. If I assume that the commutator of phi of P1 and phi star of P2, it gives me a Dirac delta. In that case, the commutator of the conjugate momentum and the field can be written in this form. Well, now I can use that Dirac delta. You see, this exponent just becomes 0. This exponent, this term becomes 0. This omega P1s and P2s cancel this one, because thanks to the Dirac delta. This becomes minus I dp1 dp2 divided by 2, these two under.
Hocam, we need to get rid of 100 because of the deltas.
Yeah. I'm just integrating over P2 now. And I have n e to the power I p1 y1 minus y2 plus e to the power minus I p1 y1 minus y2. Minus I, well, both integrals give me Dirac deltas minus I n times 2 pi Dirac delta y1 minus y2. So, and remember, this should be, I'm expecting this to be minus I Dirac delta y1 minus y2. Which tells me that this n should be equal to 1 over 2 pi.
Is it an expectation or a postulate of some kind?
This is my result. Is it?
we equated this to our expected value.
You see, what we have, we should have this condition.
Yes.
Okay.
we
And
require this, right?
well, that is the quantization condition. That is
Yeah.
that is the step where we quantize our system.
Mhm.
And then we say that on the other hand, in terms of my Fourier transformed operators, let's say, that commutator is given by this expression over here. So this is an integral equation that we have to solve. And the solution is this one. I didn't remember what n was with my convention, so that's why I kept n over there. And it turned out that n was 1 over square root of 2. So the commutation relation, I can actually write it as phi p1 over square root of 2 pi, phi star p2 over square root of 2 pi is equal to n times, n. No,
What's the symbol we set equivalent to n?
Hmm?
1 over 2 pi.
Oh, that's
N is-
fine, all right.
n is 1 over 2 pi. If n is 1 over, you see, let me go back to my definition of my field. I said that we obtained the equation that phi should satisfy. We saw that it's kind of it's a Klein-Gordon equation, so we can write it in general as dp 1 over square root of 2 omega p e to the power minus I omega pt plus I py phi of p plus e to the power I omega p of t minus I py phi star of p. Now what I did was, okay, this is my field. I can calculate the conjugate momentum to this field for using my Klein-Gordon Lagrangian. So the momentum corresponding to this field was just the derivative of phi with respect to t. So this is still just classical physics. Then we said, okay, let's quantize it. In classical physics, in the case of the harmonic oscillator, what we mean by quantization is just imposing the commutation relation between p and x. Now we did the same thing over here. This is our p, this is our x, if you like. And then we impose the quantization condition. This is my quantization condition. So, but at this step, we are already saying that, okay, phi is now an operator, pi is now an operator. They are both operators. In this expression, it means phi of p and phi star of p, they are our operators. They are operators. And they don't commute with each other. So let's look at what their commutators should be. So we start by, now we have the explicit expressions of phi and pi in terms of so-called the normal modes. We know the quantization condition. Then, using this quantization condition, I basically drive the quantization condition of this phi of p and phi star of p. And it turned out that the quantization condition for phi and phi star of p was given by this expression over here. Let me do one more step, one more redefinition, if you like. I don't like the square root of p's in the commutator. I want my commutator to be a Dirac delta function. Well, I can do that. Just multiply these by square root of 2 pi, divide dp by square root of 2 pi.
And we define phi.
Hmm?
And redefine phi.
And redefine phi so that this square root of 2 pi is also absorbed there. So with this definition, then the commutator of phi p1 phi star P2 is actually Dirac delta P1 minus P2.
So how do we show that our assumption was correct?
Well, we did show that our assumption is correct. You see,
So we assume something and found out n?
no, hold on, you see. What I did was, I made two assumptions, well, several assumptions. I said that, okay, this is my general field. I will phi p and phi star of p are my operators. Then I said that phi p1 and phi p2, they commute. And then I said phi star p1 and phi star p2, they also commute all the time. And then I said phi p1 and phi p2, they need not commute if p1 and p2, they are equal. Those are my assumptions. And then I solved that with these assumptions, I can solve my quantization condition. Okay, just hold on a moment. Now, is this unique? That's another problem. Maybe I have other solutions. But let me just translate what I had done here in terms of fields to a bunch of oscillators. This was my Hamiltonian. My Lagrangian, sorry. So in classical mechanics, if you have a bunch of coupled oscillators, what do you do? How do you solve that?
Turn them into a matrix operation.
Yeah, you turn them into a matrix operation. You diagonalize the matrices, so you just find the normal modes. And the normal modes, in terms of the normal modes, your Lagrangian is much more simplified. This is your normal mode. Well, I corresponds to the position, but in terms of the normal modes, n doesn't really correspond to position. Each xn will be just a superposition of xi's. And these are your normal coordinates, if you like. So if you create a system in one of these normal modes, your system will remain there. It's just the analog of energy eigenstate in quantum mechanics. This is what you do if you have two oscillators, three oscillators, just find the normal modes. In terms of the normal modes, your differential equations decouple. Well, this is nothing but a bunch of harmonic oscillators. Which means if I quantize them, I can write it as the annihilation and creation operators. So this will be, when I quantize them, they will become a n dagger a n plus 1 over 2 h bar omega n. What are these a n's? Well, a n a m dagger. This is Kronecker delta and m. All the other commutators vanish. This is exactly what I did in the continuum limit. Normal modes in the continuum limit are just the plane waves. So I wrote my solution, if you like, in terms of my plane waves. So basically I converted my problem into a problem of normal modes. They decoupled from each other, different points. You see, derivatives couple neighboring points in space. We will write down the Hamiltonian in a moment. If I write everything in terms of plane waves, different modes corresponding to different p, in this case, they will decouple. And just like these are the discrete analogs of my commutation relationships, the continuum analog will be phi of p, phi star of p. Their commutator is Kronecker delta p1, p2, p1 minus p2. And just like n denotes which normal mode I'm talking about, in the continuum case, it corresponds to the momentum. So p just tells me which momentum I am talking about. Specifies the momentum of this normal mode. And already in the discrete case, I know that different normal modes, they are decoupled, so they will not interact. The commutator of operators corresponding to different normal modes, they will commute. Only A and A dagger will not commute. Well, this is the analog in the continuum case. I could have just started with the normal mode analogy and took the continuum limit, but this time I wanted to avoid that, so I started with the continuum limit, calculate the momentum, impose the commutation relation between the momentum, between my field and the corresponding momentum, and the solution is this condition. All the other commutators vanish. And at least I actually did prove that this commutation relations is a solution of this condition. What we had done over here is the proof that these commutation relations solve this problem. Are there other solutions? Well, that's a different issue. Or if there are other solutions, under which conditions we have other solutions. Other questions? Yes. Which one?
The two momentum operators, P1, P2.
Which,
The
where?
end of the first one.
Here,
It was the next one.
next page.
This one. And could we give
Hmm.
those two momentum?
Yes.
By one,
Okay.
could we see?
Why two momentum? Why two momenta? Oh.
Two momentum
Yeah.
in different position places.
Okay.
The commutator like that in the previous one.
Where? I mean, this slide.
Maybe previous.
Well, this is the first time I introduced two different momenta. Since pi and phi, they are both integrals, they have their own different integration variables. Or there was also this one.
There was like two momentum operators and the result was like minus I bar direct delta function y1, y2.
Here. This is what we had at the end of the last hour.
Maybe I just confused. Because at some point I remember something like there were two momentum operators and the result was not zero, it was a delta function.
No, if I wrote like that, I wrote wrong. I mean, the non-zero commutation is the position and momentum. Okay.
Also, I guess that 2 pi can be interpreted as a circumference of the circle at unit radius, right? So the functions that we find is like they're like we can expand them like sine cosine. So they are defined on circles, so we are normalizing them. So can we say that from that perspective, it's also
I would rather not. I mean, why do we have a circle? Why should we interpret it as a circle? Well, to be honest, even this is not the convention, by the way. You see,
Doesn't it depend on the definition we use for the Fourier transform?
yeah. Usually the convention is this one. And then the commutation relation contains as 2 pi. Or, yeah, 2 pi. But let me stick with this one for the time being. In the future lectures, we might change it. But you see, the nice thing is, once we identify that, once we realize that what we are actually doing is, sorry, let me write the Hamiltonian, not the Lagrangian. When we do all these redefinitions, we are basically converting our problem to a collection of non-interacting, independent harmonic oscillators. Well, we should basically get the same Hamiltonian. You should get this one for our Hamiltonian in terms of our new fields. Yeah, this integral over.
Was supposed to be on the first part, wasn't it?
Yeah. So this should be our Hamiltonian now in terms of our new fields. Because I repeat, it is essentially just a collection of oscillators and nothing else. Well, let's do, okay, that is one thing that we need to show, which I'm kind of trying to avoid. Another thing is, you see, we calculated, looked at the equal time commutation relations. We start by quantizing our system at equal time commutation relationships. What happens if they are not at equal time? Well, nothing fancy really. You see here, the commutator will again be given by this integral. But instead of all the exponents having a time t, it will be t1 and t2. We already know what the commutators of phi and phi dagger are. You can just place it over there. You will get an integral representation of non-equal time commutation relationships, and they will be non-zero. There won't be Dirac delta. Well, that's also shouldn't be a big surprise. Remember your quantum mechanics courses. Even if you say that X and B commutator is I, if you use the Heisenberg picture, in quantum mechanics you say X and P is I times I. In Heisenberg picture, at different times, they won't be just I. X at different times, it won't be just 0, they won't commute. P at different times, they won't commute. Well, the same thing happens over here. Phi at different times will not commute. By the way, my quantization condition is not just this one. My quantization condition, I also have these conditions. This should be 0, the same for pi. So all these conditions, you can use all these conditions to prove that this is actually your only solution in this case. There are no other solutions. Let's calculate the Hamiltonian. I have my Lagrangian, which was dy 1/2 phi dot squared minus 1/2 phi prime squared. It should be m squared. I probably made a sign mistake somewhere. This is my Lagrangian. To calculate Hamiltonian, first I need to find the pi, which I already did. This is phi dot. And the Hamiltonian will just be dy py phi dot minus the Lagrangian, which will be dy 1/2 phi dot squared plus 1/2 phi prime squared plus 1/2 m squared phi squared. And this is my Hamiltonian. I already know what phi is. Okay, so all of those terms contain two integrals, two momentum integrals. So let me just write dp1, dp2 divided by 2 pi. Each one of them has a square root of 2 pi. And then I have a square root of 2 omega p1, 2 omega p2. Let me cheat a bit. I'm really too lazy to do all this computation.
Maybe it can also be exercise
Hmm?
for the next lecture.
For the next lecture, no. It can be an exercise for you to do at home. I mean, I leave it to you as an exercise to calculate the non-equal time commutation relationships. Now, I can calculate. I do have a cheat.
Can you write down
Hold
the
on.
exercise you just said?
Hmm. I did an integration by parts.
I think that should be also plus.
Which one? The last one.
Second one.
Here it should be plus, no?
Then the x derivative term.
Oh, sorry, hold on. The x derivative term is a minus, but keep in mind, there is a term I'm missing.
In the second line.
I don't have a t integral in my Hamiltonian. So I cannot do an integration by part in t. So that will give me plus dy minus del by del t of phi del phi by del t. No, plus. Y, if you take this derivative, I have the with a 1/2, right? Well, if you take that derivative, you get the second derivative squared. That is this term over here. Then I get an additional term of phi times the second derivative of phi. This will cancel this term. So if I add these terms, at least the time if I add this one and this one, the time derivative term will just give me this one. In terms of y, I just do an integration by parts. I can do that because I'm integrating over y. This term remains as it is. This is the term I get after integration by parts over y. The nice thing is that curly brackets is 0. It is 0 because it's the equation of motion.
can't see why the second term is minus.
No, it's not.
Which one? This one? Well, I started with this one.
No. Just at the last line,
Yeah,
the second term.
This
del
one.
square phi over del y square.
this one.
The one below.
That is plus.
Well, to get a minus when you factor out a minus phi, you should have a plus in the previous line.
Hold on. This is my Hamiltonian.
Yes. After that line, that would be plus 1 over 2 phi.
No, that's correct.
Now this is.
That is correct. Then the
Hold
the
on,
other
hold on,
part
hold on, hold on.
minus.
Let me write the trick and then I will leave the rest for your homework. The first term is 1 over 2 del over del t phi by del t minus 1 over 2 phi del squared phi by del t squared. This is the first term. Let me even not do that. Because eventually that term will remain. This is 1 over 2 phi dot squared. I can do that trick in the second term. Integration by parts. Then I have 1 over 2 m squared phi squared. I just did an integration by part. Minus 1 over 2 phi minus del squared phi by del y squared and minus m squared phi. Right? Now I can use the equation of motion. Equation of motion should tell me that that term is
Isn't it plus? Last line.
which one?
Phi over del y.
This one, this is plus, yes. Now, from the equation of motion, I have this one. Or and well, I will be happy with that.
Maybe now we can do integration by parts.
No, I mean we cannot. I'm not integrating over t, so there's no integration by part here.
Yeah, I mean, by integration by parts,
Yeah.
I mean taking the derivative.
The first term will be if I take this derivative, it will be the first term derivative, and the additional term is minus 1 over 2 phi del squared phi by del t squared. Let me see, what was the equation of motion? We have del squared by del t squared phi minus del squared phi by del y squared. I am getting this sign of m squared wrong. This should be equal to 0. So this should be plus. I will check my signs. Then I have this plus 1 over 2 phi del squared phi by del t squared term. And these will cancel. We are left with the first one only. I'm not so happy with the 1 over. No, I'm happy with this. Okay, if you do the steps, what you will get eventually, you see. There will be these two time derivatives that will bring down factors of omega p within the integrals. And, no, okay. Let's do this as an exercise. Okay, I always get this sign of m squared wrong. This should be the final answer the time derivatives will bring factors of omega p. In your measure, you already have 2 omega p1, 2 omega p2. You see, each one of these time derivatives will bring an omega p1, some factor of omega p. There will be 2 of them, so you will get omega p squared. You will get Dirac delta omega p1, p2s. So Dirac delta p1, p2s by y, due to y integration, because they are at equal times, integrating over y will give you Dirac delta p1 minus p2. So this will cancel one of them after you evaluate one of the integrals. So you will end up having dp1 omega p1 phi p1 phi star p1 plus phi star p1 phi of p1 at the end of the computation. Okay. It will be, it is straightforward, but it will be straightforward, but it will be long. I'm just too lazy to do it now, so for your own exercise.
Can I ask a teaser question?
Hmm?
This phi's, I mean, we already identified them with the creation and relation of it. And if we use the commutation relation between them, what we get is a dagger a plus some constant. But this is under integration and it gives us some infinity. What's the meaning of that?
Here we have this 1 over 2. Here we have an integral over p from minus infinity to infinity, which is infinite energy. So we have a system. Well, this is practically the first time we meet this infinity. Well, the same holds for infinitely many oscillators. Each oscillator has a minimum ground state. Ground state energy is non-zero. So the sum of this energy over all the oscillators gives you infinite energy. Well, I will cheat. I can always shift the energy by a constant. So I can shift the ground state energy of each oscillator to 0. That is basically getting rid of this 1 over 2.
I'm sorry, can you explicitly write what you left for us to do at the end of the PDF?
So show that any other questions? Okay, on Monday we don't have a lecture. This Monday.
Why?
Hmm?
Do we have an exercise class?
No. I mean, I haven't given you any exercise problems except on this one. I don't want to just give it now and ask you tomorrow or in 2 days. I don't want to solve these on the board. It's boring. It's straightforward, but boring. So we will skip next week. The following week we will have a problem solving hour.
Week or just Monday?
No, you see, we are supposed to have 6 hours in 2 weeks. This week we will have 4 hours. Next week we will have 2 hours. In the following weeks, I will use this alternating Mondays as problem solving hours. So we will
benefit for all 4 hours in a week.
I will use all 4 hours.
So every other Monday is a problem session.
Every other Monday will be a problem session.
Bir şey sorabilir miyim?